of the fourth session, the active fire phase of the Wildland fires. It will be last from 9 a.m. to 1 p.m. Eastern time in the US, so about 4 hours. Um, Before we begin, I'd like to thank the Satmoc working group, including myself, Jun Wang from University of Iowa, and also many other members, in particularly Gary McWilliams has been leading this working group for a while, and we have been working on this since early January, and as well as Megan Christian, who has been hosting the session, and also many others from the different universities and the NOAA Corporate Institute. So today we're happy to have our invited speaker, Dr. Meng Zhou, who is an assistant research scientist in the NASA's GMAO, as well as the University of Maryland, Baltimore County GISTAR. I think the GISTAR and the Goddard Space Flight Center has a mutual agreement, which Meng has been working on the project, including the GEOS Earth System Modeling, GEOS ESM, as well as NASA's Fire Science Technology Program. Meng received his master's degree in information and computer science engineering, as well as the master's degree in informatics and a PhD in geoinformatics from University of Iowa. He actually was one of my former outstanding PhD students. I know him very well. He received several awards from the American Military Society annual meetings for his presentation, for his work in nighttime remote sensing of fires and aerosols. So before I give the floor to him, I have two announcements. One is that the NOAA Satellites Hackathon is coming in October 2025. Feel free to scan the QR code in the bottom right there, and from there you can join this competition, and there will be awards. But before you think about awards, you think about other things as well. We will have a group of the subject matter experts and mentors to help you along the way to join this competition, to help you to solve problems, and there are very practical, also hands-on problems that you are going to gain help and support from a group of scientists and mentors there. So feel free to attend that. And finally, all the presentations of this short course, all the 4 sessions will be will be recorded, and they will be posted on the website there that you can access. And then from there, you can also access the YouTube channels where all the recorders are recorded there. And there are also questions that the QA sessions that you can direct the questions through the Zoom function called Zoom QA functions there. And with that, Meng, the floor is yours.
Okay, yeah, thank you, Jun. Let me share my screen. Yeah, so I believe everyone is seeing the slides in a good shape. So hello everyone. So my name is Meng Zhou. So welcome to the AMS Satmoc short course. So today is a third session. So we will have a brief review of all the active fire technologies, basically spaceborne active fire detection technologies that has been used widely in recent years. So here again, it is myself. Let me turn off the camera to save some bandwidth. Yeah. So first about myself. Of course, my name is Meng Zhou. I'm working for NASA Global Modeling Data Simulation Office at Goddard Space Flight Center. So my main project is developing satellite-based wildfire detection algorithms and also satellite-based biomass burning emission inventories to support the NASA geosystem work and also NASA's fire sense technologies. So my email is listed here. So after this presentation or this course, if you have any questions about anything we come across today, you can email me. Yeah. So today we will basically have 4 topics. So first we will have a brief overview of the space-borne fire detection technologies, because as you know, detection of wildfire from space has a history of almost 40 years. So there are a lot of sensors and also a lot of algorithms established for the past 40 years. And we will go through the basic principle of those detection algorithms. And then we will talk about 2 newly advancement of the fire detections made during the past 5 or 10 years. That is firelight detection algorithm, and also, we will discuss the impact of the atmosphere to the characterization of the fire radiative power. At last session, we will do some hands-on practice. So I will provide you some Python script. We will use those script to practice on how to access data from NASA labs data repos, and also we will see how to map fire events from those data we will acquire we required from NASA. So as you know, fires as a response to the climate change, wildfire happens more frequently for the past decades. So the impact of fire is multi-phased, from the local scale human risk and property damage to the regional scale air quality issues and visibility reductions. Eventually, wildfire will contribute to the global scale climate change again, and they are some kind of boosting each other. So as you can see, for the past decades, statistic or satellite observation shows there is a positive trend of the wildfire occurring in both detected, the number of detected fire events, also the total energy, we call it fire radiative power released to the space. So you can see the big increase, occurs over the North America, over Siberia, and also Australia. Those areas are suffering from those arid or dry conditions due to the climate change. So here, if we take a closer look at North America, so you can see here are all statistics made by the EPAs. So you can see there, comparing to 40 years ago, let's see, from 1980s to 20s. So for the past 20 years, which is from 2000 and until now, the burn area caused by wildfire increased dramatically. Almost, for example, if we compare, the early 1980s to now, you can see, we almost double or triple the burn area, from caused by wildfire. So you can also see, the occurrence of the wildfire, mainly the increase of the occurrence of the wildfire, mainly clustered over the west coastline, which we know they are dry in the summer and in the winter. So you can also see, from the lower right panels, the burn area mainly happens, the burn area over the past 20 years, actually, as we discussed, is almost tripled, compared to the early 1980s to 2000. So if we further look at the California regions, because you can see, here, California is one of the states that suffers from the wildfire a lot, for the United States. You can see the changing climate actually favors the growth of the wildfire. So if we look at the meteorological conditions, which is temperature, fire weather index, which is calculated from a lot of meteorological parameters such as temperature, field moisture, soil moisture, and wind. So you can see all those parameters that favor the growth of wildfire actually increased for the past 20 years. In the meantime, the precipitations also dropped, over California for the past 20 years. As a result, you can see the burn area for the autumn seasons over California actually dramatically increased. So there are a lot of consequences for fire events if it happens. So one of the major concern is it will cause a lot of public health issues. So the long range transport smoke will greatly degrade the air quantities and consequently affect people's health conditions. So you can see here is example of wildfire cases happens in 2023 over the Canada, and after long range report, those smoke eventually hit the eastern part of the United States. So you can see here these are photos taken from the DC area, Baltimore area, and New York area. So you can see how those smoke attenuate the lights and then makes the lights, not blue anymore. And you can see the red sky, and you can see the haze, and of course those haze, after you breath those haze, it will enter your body system and cause a lot of problems. And and sorry. So here is animations. Here's the animations that illustrate how the smoke transport from the Canada to all the way to the north to the United States. So it happens in the last year. Is one of the largest wildfire events, and impact a lot of areas, the air quality of a lot of areas. Yeah. So wildfire also impose some impact on the climate system. So for example, wildfire can create its own environment, and then environment in the fire weather environment. If the fire is large enough, it will eject the smoke into a very higher altitude. So in that case, we create clouds. So in that case, we call the clouds created by large fires and injected into a high altitude cumulus nimbus. So you can see after ejected into a higher altitude, let's say troposphere, the smoke can stay in the stratosphere for a long time. And it will bring some interesting effects to the climate system. So for example, here what we are showing is a wildfire happened in British Columbia in I think in 2017. Uh, 2017. So you can see after long range port, the smoke after injecting into the stratosphere, the smoke actually transport all over the world. And then after a certain amount of days, so you can see even a single parasitic cases, it will increase the radiative forcings, yeah, to an extent, and to some extent is a significant extent, which will boost the climate, the global warming again. So if we are encounter wildfires, so what we should do, of course, is call 911. I brought this here is because when I talk with students in UMBC, I ask them in my universities, I ask them if they encounter a wildfire events, what should they do? And they say they will go and try to kill the fire. But actually, it is very dangerous. If you happens and unluckily, run into a wildfire events, just call 911 and let the professional guy and deal with the wildfire events. So the question becomes, how can we sense a fire from space? So here, what we are showing is a global fire detections from the VIR sensor, for the year of 2019. So you can see wildfire happens all the time and globally, and you can see on those pop out events, that is fire that are extremely large. So how can we achieve those fire detections from space? So you can see detection wildfire from space has long histories. So actually it can be dated back to the early 17th. So this in here, what we are showing is a first fire detection from space made in 1973. It is, you can see, well, we can actually, even, back to 50 years ago, we can see the fires or gas flarings, which is eventually a fire events from space. So at this moment, we are using the visible light because glowing or emitting lights is a natural properties of the wildfire events. So where is fire, there is fire, there is light emitted. So in fire detection, algorithm development aspect, three people actually we should be memorized. So first one is Dr. Jeff Dozier. So he's the first guy, who proposed to use satellite, or he's the first guy who used a satellite to detect fires from space. And then is Dr. Joran Kaufman. Yeah, this is for the US era. So they designed the most famous MODIS sensors and use a MODIS sensor to detect fire. And the MODIS active fire product is one of the most popular spaceborne fire detection product used for the past 20 years. And another researchers is Dr. Martin Worcester from King's College London, and he proposed a method to parameterize the total energy the total energy released by wildfire events. So since then, we are able to know how large the fire could be from the space. However, in order to understand, how can we achieve fire detection from space, we need to know from the physics and chemistry aspect. So you can see, Dr. Faraday, concludes there is no differences. There's no differences comparing to when comparing candle lights with a wildfire, which is pretty true. So you can see when we consider wildfire events, the process is basically the after ignitions, the heat released will evaporate the moisture in the fuel. Then the fuel will go through the pyrolysis process and release those flammable gas, and the flammable gas will be consumed and release more heat, and those heat will in terms to evaporate the fuel again. So basic combustion process is a self-sustained process. So as a wildfire events. So how can we model wildfire, or at least what is a mathematical model for wildfire in terms of satellite remote sensing? So we have three scenarios here. Let's see. So in the first scenario, there is no fire. What can be sensed by the satellite is a pure background. A sickness scenario, let's see. So there is one big fire event, and then we can assume, okay, in this background, or in this area, we have two temperature components. One is from the background, another one is from the wildfire. But we know for large area, the fire events is not the fire events can be a complex events. It's a fire complex. So we may, in the third events, we may have more components, fire components. So you can see we are not only have the fire background temperature, we have multiple temperatures that are used to represent the temperatures of a combustion process. So the question is, what is the law that relates a temperature to the radiative heat released from the wildfire? So the answer is pretty straightforward. It's a Planck's law. So using the Planck functions, we can calculate the spectrum-dependent radiance of each temperature. So you can see the physics and chemistry of the combustion, such as the fuel type, oxygen availability, and combustion phase determines the connected temperature of the flames. And those temperatures in terms governs both the total and the spectrum distributions of the radiative heat. So understanding this, we can model the radiance received by the satellites into this form. For the first case, because we only have the background temperature, we will only use one terms, that is a Planck function, to represent the radiance. So for the second case, because there is one more temperature component, so we add another term here, because you can see wildfire will take occupied some area of the background. So you can see we use the fractional area to represent the fractions that wildfire occupied on the ground. Of course, if we have more components, we can add more terms to the radiance. So with that, how can we detect wildfire? So basically, you can see this term is contributed by the wildfire. right? So the first principle for spaceborne fire detection is detection of anomaly. How can we determine a spatial anomaly? So here, I provide you guys the 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 first principles. So what we do is we have spatial observations uh, from the ground, and then we can use a spatial window to select those observations that we can determine. We can 100% guarantee that are clean. And with that, we can what? We can derive the mean and some statistics, for example, the mean, the standard deviation, the MADs of the background. With the mean and the background, we can form the spatial probability detectors, which means we know the means of the background temperature, and we also mean the variations of the background temperature. In this way, we can form, for example, under the Gaussian assumptions, we can form probability filters. Usually, we use the 3 sigma rules. Say if the radiance observed from some point is way beyond the 3 sigma regions, which is 0.999 in probability, 0.999 in probabilities. So we will view it as an anomaly. Then in this way, we can select those anomalies, and for the most of the cases, those anomalies are caused by the wildfire. We have come through the basic mathematical principles of the fire detection. The question is, which wavelengths should we choose? Because as you can see, what satellite from the space can sense is a radiance of each wavelength. The question is, which wavelengths should we choose? So let's look at this image. So this is an image. This is a spectrum image of wildfire events, of several wildfire events. So for example, the green line is a pure wildfire signal with 1% area occupied by a 600-degree fire events, and 0.1% occupied by a high temperature component, which is 1100 kelvins. On the other hand, we have the black line represents the solar spectrum, and upon that, we have orange line that represent the sunlights plus the background plus the fire signals. So if I ask you, you are assigned to design a sensor to conduct the fire detections. Which channels? So from the visible all the way to the thermal infrared. Which channel would you like to select? So usually, the principle is we need to find those channels that are mostly sensitive to fire signals, and also avoid those contaminations from, for example, ground or sunlights. So you can see over the spectrum of 4 microns, fire signals are most distinguishable because the sunlights has very little contributions comparing to comparing to the firelights. And also the background temperature, let's say it is 310K, is very is very low, excuse me, is very low in radiance comparing to the fire signal. So that is to say 4 microns is so 4 microns should be the channels select. So let's look at some real data to see whether it is correct. So here, what I provide you guys is nighttime and daytime observations made by the VIIRS sensor on board the Sumin PP satellite. So I hope the font size is large enough. So you can see the spectrum radiance is from 0.8 microns all the way to the 12 microns. So because we've already know from here, 4 micron might be the best channels for the fire detections. So let's see here. This one is a 4 micron radiance made at night. And here, this one is a 4 micron radiance made in the day for wildfire events. So you can see here, for other channels, for example, shorter channels at 1.6 or 1.2, at night we can still see some signals. We can still see some fire front. However, during the day, as we show here, the sunlight is way stronger than the firelights. So you can see observations made during the day at those channels 1.2 and 1.6, we can barely see the shapes of the fire events. On the other hand, you can see for those longer wavelengths at night, we can see some of the signals. However, you can see at the longer wavelengths, for example, 12 microns or 11 microns, we can barely see the fire front from the 11 or 12 microns. So this verified, our conclusion here. 4 microns are the most useful channels we should use in fire detection. So actually, the 4 microns together with the 11 microns are the gold channels in the current MODIS and VIIRS standard fire detection algorithms. This is because we need one channel that is sensitive to wildfire, and we need another channel that is more sensitive to background in order to support us to select those clean channels or to select those clean pixels, which allow us to form the statistics of the background in order to further form the spatial or probability detector. Yeah. So here is a basic. Here we have the basic principle of fire detection. We use a 4 micron and 11 micron observations to conduct anomaly detections in order to achieve wildfire detections. The question becomes, is it enough for us to know the location of the fire? So let's see if the fire is very small. Of course, every wildfire is some kind of bad. But if we have two fire events, one is large, one is some kind of small. For firefighter, which one should we kill first? if we only have the location, or if we only have the information on the locations of wildfire, it will probably be hard for us to determine which one should we first to which fire should we suppress first. On the other hand, what kind of information do we need to know about? What kind of additional information should we know about the wildfire? Specifically, for air quality or weather forecast purpose, you know, what kind of information should we know to support the forecast of smoke? For example, as we showed before, National Weather Weather Service and NASA provide a daily smoke forecast. What information should we know, should we have, or should we ingest into the weather forecast model to enlighten it? There is smoke, and we need to consider it. Okay, the information we need to know is fire radiative power. So as you can see, fire radiative power is a measure used to quantify the rate of energy emitted from a fire. So it captures the total radiative energy released by a fire per unit of time. And it is in a unit of power. It's watt or megawatts. Okay, so from the Stephen Boltzmann law, if we know the temperature of combustions and we know the area of the combustions, we can actually calculate the total energy released by the wildfire events, through the Stephen Boltzmann law here. So you can see usually the power is proportional to the first orders of the temperature. However, for satellite, in terms of satellite remote sensing, what we can sense or what the satellite sensor can sense is a radiance. So basically, it is hard for us to know the actual temperature of wildfire events, and let alone, we still need to know the area, how many acres or how many square meters of the ground is burned. So basically, it is very hard for us to know the temperature and actual fire area from the remote sensing aspect. So Martin Worcester, then come to approach. So what he did is he conducted analysis to the spectrum radiance with a Stephen Boltzmann curve. So you can see here, he did several regression lines towards the different channels of radiance and towards the temperatures. And what he found is a 4 micron. Again, we jump to the 4 micron problem again. Yeah, the 4 micron radiance is proportional to the fourth order of the temperature closely. So you can see here what he concluded is the 4 micron radiance sensed by the satellite is some kind of proportional to the t to the fourth. And magically, t to the fourth is used in the Stephen Boltzmann law to calculate the FRP. It is by definition. It is a nature. Then again, magically, Dr. Martin Worcester conducted some regressions to relate the 4 micron radiance to the FRP. So you can see here, there is a logical chain here. We have 4 micron radians is proportional to the t to the fourth order to the fourth, and then we can have t to the fourth and proportional to the 4 micron radians divided by a regression coefficient. And if we decorate the temperatures with the Steven Boltzmann constant and also decorate it with the total area of a satellite pixel, then we are actually able to calculate the fire radiated power based on the 4 micron radians. So what can we use to what can we use how can we use the fire radiated power? So Dr. Wooster and Dr. Achujo conduct research on the relationship between the total radiated power and the biomass burned. So you can imagine, so if we burn 1 kilograms of grass, so they will release a certain amount of energy. And if we burn 2 grams or 2 kilograms of grass, and it might release the double energy, compared to 1 kilogram. So what they found is the FRP, the fire radiated power, is a good indicator of the biomass burned or biomass consumed. So you can see here, this figure is from Dr. Wooster's one of the Dr. Wooster's paper. So what they relate is the total radiative power or radiated energy, and with the weights of the biomass burned in a fire event. So you can see they show a very good correlations. And also further, Dr. Achujo also demonstrate in different area, for example, in Canada, in Brazil, and in Africa, the relationship in between the FRP and the biomass burn is some kind of robust. So from then, fire radiated power has been widely used. Sorry. Fire radiated power has become a widely used a proxy of the biomass consumed. So if we know then from the FRP, then we can scale it to how many biomes it is burned. Then with a biomass burned, we will know, for example, if we assume if we burn 1 kilograms of grass, it will release 1 grams of carbon monoxide. Let's see. Then we will be able to know what that is the emission factors. We will be able to know how many species, for example, smoke, is actually emitted from the wildfire events. So this is pretty important, and actually, this relationship or this formula is a foundations for the fire emission inventory. Basically, is top-down fire emission inventory used by a lot of fire weather forecast system. For example, the ECMWF, the European system, and also the NAPS, which is used by the Navy, and the and also the QFAD, which is used by NASA. They are all greatly rely on the FRP to estimate the total mass burned by fire events. However, For the past 40 years, the majority of the fire detection is conducted based on by the polar orbiting satellite. For example, MODIS and VIRS. So they do have some problems. So MODIS and VIRS is a whisker brood system. So that means they will use these rotating telescope assemblies to scan the Earth, accordingly. Because of the curvature problems of the Earth and also the view geometries, the scan properties of the satellite, there will be the distortions towards the end of the scans. So you can see here, at the nadir, which is right below the satellite view, the pixel size is smaller comparing to the end of the scans, which you can see here. We have around 4 times differences. So what can these distortions impact? So that is, we call the distortions the bow tie effects. So you can see here again, this figure shows here is a nadir views of the satellites of satellite observations, and here this is the end of the scan views. So you can clearly see the area covered at the end of the scan is way larger than the nadir. It has a bow tie shape. So that's the reason we call it the bow tie effect. So then you can see, so if we, in order to cover the Earth's ground, seamlessly, so what we are expecting is, we need to have, a continuous observation at nadir, and then there will be overlap. At the end of the swath. So what it mean by there will be overlap at the swath? So here what you can see is if we directly plot the image plot the image into a graph, you can see here, you can see clearly this is a river, right? And here is we directly show the image without projected on a map. So you can see there is a repeating patterns. So which means in different scans, those areas are observed by the satellite twice at the end of the swath. What does this mean to the fire detections? That means if fires happens, for example, at these regions, the regions unpointed, and it will also be detected at here. That is which will cause the double countings of wildfire. So you can see here. Let's first look at here. So this is a this is a fire detection made by some standard product. You can see over here, over these regions, very top right regions, we can only see single dots. Those dots are fire detections. There are no overlaps. However, at the green box, red box, and orange box area, in those areas, you can see some dots actually are overlaid with each other. So if we further look at those unprojected area, you can see the repeat patterns. For example, here, these regions, actually are exactly the same as these regions. This is what we call, the bow tie effects or double countings, because those fires happens at those regions at the end of the swath, and it is it is viewed, or it is scanned by the satellite sensor, twice into continual scans, and the time differences is just maybe 1 second or even shorter. So basically, they are the same fire events. However, if we don't handle it, we will count those fire twice. So in fact, the double counted fire in the standard fire detection, in the standard fire detection product is large, is around 20%, and also the FRP calculated from those double counted fires is around 840 gigawatts, which is also around 20%. Considering, if we use these equations to calculate for example, the carbon monoxide or carbon dioxide released in the atmosphere, if we don't treat the double count if we don't treat the double counted fire carefully, we will release more smoke and trace gas, for example, CO and CO2 into the atmosphere. That will introduce a lot of uncertainties in the downstream weather forecast, or hazardous monitorings. Yeah. So in the next section, I guess we will talk about the new product, and we will also talk about how those problems is handled. So I guess we will take a break here. So if you have any questions, you can ask in the Q&A session. Otherwise, we will have maybe 10 minutes break. And during this break, I do want to do one thing, that is to register a free account at NASA Earth Data Search. So in our hands-on practice, we need to request some data, near real-time data from the NASA Earth Search. Yeah, thank you. We will come back. We will come back at 10:10. Yeah. Yeah, Megan. Hello everyone, welcome back. This will be the second session of the second part of the session 3 for the AMS Satmoc short course. So in this subsessions, we will talk about the recent advancement in fire detections. So specifically, we will talk about the firelight detection algorithm FILDAP. So in the last session, we overview the principles of the fire detections. So we have a conclusions. 4 micron is a golden channels for fire detections. We greatly rely on observations from the 4 microns to sense the fire, and we also come across with the mathematical principles for fire detection is detection of anomalies. We use a clean background observations to form the statistic filters in order to detect fires on the ground. So so as we say, this fire detections will only provide us the locations of the fire events, and also it will provide the FRP, which is the total energy of the fire events. And we further come across the FRP actually is a widely used proxy to measure the biomass consumed to in a wildfire events. However, as you can see, if we want to know what kind of species, how many CO or CO2 or carbon or NOx are emitted, we still need to know the emission factors of the emission factors of the events. So, however, as you know, the emissions from the wildfire depends on the combustion phase, which is a function, or which relies on the temperatures of the fires. So you can see in this graph, in different combustion phase, the fire will emit different things. In the flaming phase, most of the carbon will be converted to the carbon dioxide, and we call it the complete combustions. But in the smoldering phase, because the participations of the oxygen is limited, so only part of the carbon will be oxidized it will be fully oxidized into the carbon dioxide, and a lot of them will remain partially oxidized, which will be the carbon monoxide. And also because the combustion chemistry will be different, the released volcanic compound will be different, and so as some other parameter, so as other emissions. So here we summarize the combustion process, or the combustion product for different temperatures. So you can see when the burning temperature is low, it is in the preheat or slow pyrolysis process. Sorry, in the preheat or pyrolysis process. So you can see at these temperatures, there will be aromatic compounds or methane emitted, and also lignins and hemicellulose is decomposed. If the temperature increase, materials released by the lignins and hemicellulose will be converted to the carbon dioxide, carbon monoxide. If the temperature keep going up, which means more oxygen is participate into the combustions, and the carbon monoxide will be further oxidized into the carbon dioxide, and other emissions such as NOx and SO2 will also be released. So what controls the combustions? Here we come back to the physics again. So usually we use combustion efficiencies to measure how the completeness of a fuel that is oxidized or burned. So basically, the combustion efficiency is defined as the amount of the carbon emitted as a CO2 divided by the total carbon emitted in a wildfire events. Those total carbon include carbon dioxide, carbon monoxide, and the methanes and other particulate matter such as soot, black carbons, char, tars, So you can imagine if the combustion efficiency is high, the majorities of the carbon will be converted into the CO2. And if the fire is more like a smoldering fire, um, the main product of the combustions might be the COs. However, you can see combustion efficiency is 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 defined by the total carbons consumed. So in remote sensing or in field campaigns, uh, limited by the capabilities of the instrument, we may not be able to measure all the carbon released. For example, we may not be able to measure. We can measure the soot, but we may not be able to measure the methane. We may able to measure the methane, but we may not be able to measure the black carbons. So in the field, we come up with another parameter called modified combustion efficiency. What we know is, we can easily measure the CO and the CO2. I'm sorry, here is a typo. So the modified combustion efficiency is defined as the ratio between the fire released CO2 to the fire released amount of to the fire released CO plus CO2. So the beauty of the modified combustion efficiency is that it is a very good indicators of the emission factor, which is the beta terms here. So you can see in those field campaigns, researchers have found the modified combustion efficiency. We will call it MCE later. So the MCE is highly correlated with emission factors. For example, here is organic carbons. So you can also see a change of MCE by 0.08 can lead to the change of the organic aerosol organic carbons by a factor of 10 or even larger. And also you can see the MCE is the MCE also has a very high correlations or with optical properties of the aerosols of the smoke. So you can see higher MCEs will have lower single scalar albedos compared to lower MCE, in this case. So how can we measure the MCE? So what we know is the current the existed fire detection or in the existed fire detection algorithms, we can only know the information on the presence of the thermal anomaly, which is the location of the fire, and the total strength of the fire, which is the FRP. And it does not have the information on what is the combustion phase of the active fire. So let's look at here again. So what we know is the combustion efficiency is a measures of the participation of the oxygen. If there's more oxygen involved in the combustions, the combustion efficiency will be higher. On the other hand, if more oxygen is involved, that means the oxidation is stronger, which means more heat will be released. That means a higher combustion temperature would be for more flaming combustions. So you can see here, from this figure, several, in the last session, we come to the conclusion that 4 micron is a golden channel that can support us to conduct the fire detections. And how can we squeeze out the informations of those channels in order to know the combustion efficiency or modified combustion efficiency? So if you have some background of the satellite remote sensing, there will be a very famous index, what we call the vegetation index or ND normalized vegetation index that use two spectrum, the contrast of two spectrums or two channels to distinguish the greenness of the vegetations. Here, we some kind of borrow this idea. So you can see for different temperature combinations, the green line is a more flaming combustion because the flaming because it has a larger flaming areas, and the red line is a relative smoldering combustion events because the high temperature component is only 0.01%. So what you can see here, the ratios between these channels, the ratios, for example, between several channels for these two events are different. For example, for the flaming signal, for the flaming events, which is indicated by the green line, the ratio between the 4 microns and 2 micron is mostly flat. And for the smolderings, you can see a positive, slope. However, over the visible band, you can see for the flaming combustions, the ratio between, for example, 1.6 and the visible 0.5 band, 0.5 microns, the slope is larger, and the ratio for the smoldering case is smaller. So with that, we might be able to know the combustion phase by contrasting some band. For example, the 4 microns with visible band, or the 4 micron with the 2.2 microns. So what we did is we use visible informations, which is at the which is around the 0.7 microns. It is from the Vir's day-night band, which can sense the visible light at night globally. So, for example, you can see here it is Vir's day-night band observation for fire events happening in 2021. It is a Coda fire. So the black image, the first image here shows here is an image sensed by the Vir's day-night band, and here is another is a climatology, which is a multiple days mean of that area. You can see here, for the fire events, during the fire events, the combustions will release a lot of visible light, and then we are able to based on the observations at the visible band, we are able to derive a parameter called the visible light power. So that is the radiative power in the visible band during a fire pixel. And of course, we've already have the total energy, total power or total energy. That is what we just mentioned is FRP. And it can be directly derived from the conventional 4 microns. So then we will have we'll have a quantity over here, we'll have a quantity over here. Then we take the ratio of the visible light power and the FRP. We define another parameter called the visible energy fraction. Basically, it is an indicator, it is an index tells you what is the fraction of the energy that is distributed into the visible band. So you can imagine if a fire is small but has a very high temperature, there will be more energy distributed in the visible channel. Consequently, the VEF will be higher. On the other hand, if the fire is cooler, and there will be lesser energy that is distributed in the visible band. Consequently, the VEF will be lower if the FRP are the same. So what we found is actually the FRP is not a necessarily good indicator of the flaming and MCE. But VEF, because it is taking ratio and is the index of the energy distribution, VEF itself is a good indicator of energy distribution. So what you can see here is we correlate the VEF, the visible energy fraction, with the modified combustion efficiency measured on the field campaigns. So you can see, in different regions and in different regions or in different land surface type, the visible energy fraction is highly correlated with the modified combustion efficiency, which means VEF is a good indicator of the modified combustion efficiency. So with these findings, we come up with this fire light detection algorithm, FADA2. So we rely on the visible channel observations from various daylight band with other I-band 4-micron observations. We conduct fire detections, and then we estimate the MCE for each of the wildfire events. In this way, we're able to know not only the total strength of fire events, and we will also know the fire phase, whether it is flaming or smoldering, and further we will know what kind of emissions for each of the fire would have by combining the FRP and the MCE. So we've also talked about, in the last session, we've also talked about there is some problems in the existed fire detection algorithm that is bow tie effects. The bow tie effects basically is a double counting of a fire of fire events. So this is big. The bow tie effects is caused by the pixel growth of the whisker brew sensor. However, you can see here, this graph compares the pixel growth of different various band of the different various sensor, the N band, the daylight band, the I band. So you can see here for the various N band observations, the pixel area increase at the end of the swath. That is what we that we already come across. However, for the various daylight band, you can see it successfully sustained near constant pixel size. So this is because, as we mentioned, let's go back here. As we mentioned here, so the N band, which is the golden channel, the 4-micron N band, is a golden channel for fire detection. However, it is a one-dimension linear detector. So that means it will only have one detector that allow the satellite to sense the ground. However, the VIIR's day-night band operating at the visible band is a 2D CCT, is a 2D camera. For a same area, it used 250 times 672 detectors to conduct the image, to make the image. This means, for day-night band, it will have more degree of freedoms to conduct the onboard aggregation. For example, at nadir they might use 200 sub detector to form one image or to form one pixel. At the edge of the scan, they use lesser subpixels to form a pixel. In this way, they are able to keep a relative constant pixel size. So you can see here, what we are showing is the red boxes are the M band scan line, which has a bow tie shape, so smaller in the nadir and larger at the end of the swath. However, for the day-night band, which is shown as green boxes, there are some kind of constant. So in this sense, the day-night band scan line actually can be used as a reference, frames to conduct the bow tie detections. So basically, you can see if there is no overlapping between the day-night band and the M band, those area will be treated as a bow tie affected area. That means, this area will be overlap with another M band. Yeah. So this is a way, we detect the bow tie effects and remove those bow tie affected pixels. To illustrate this process, let's look at this graph again. So you can see, as we discussed, for example, the orange boxes on the upper graph has a repeat counterpart in the lower graph. Also, you can see, the repeat pattern is also highlighted in the red boxes. There are some kind of repeat. So when we map those pixels into a real Earth surface, you can see, those repeat patterns actually are overlaid with each other. And with if we use the VIIR's day-night band frame as a reference frame to remove the residuals or remove the bow ties, you can see those double counted pixels are gone. For example, here you can see there's no over the last three lines. Actually it is last four lines. There is no overlappings. Also for those gaps, there's no overlapped 5 pixel anymore. So this significantly reduce the double countings of fire. So the fire detection, the firelight detection algorithm FADA2 is right now is a standard product. So it it has been through rigid validation process. So for example, we conduct validations against the high resolution aster detections. So aster images. So the aster image has a 90 meter resolution, which is way higher than the 750 meter resolution of VIIRS. So you can see this in this swing plot. There is a tiny fire events. You can see the shape. It's some kind of a crown shape of a fire events. That is 5 kilometers away. That is 5 kilometers away from the bulk of fire front. And among all the fire detection algorithms, only FADA2 or FADA2 algorithms is able to detect those small fires. For the standard active fire product, it has no detections. On the other hand, as I said, the beauties of the FADA2 product is that it can provide the individual MCEs for each fire spot detected. So we validate the FADA2 MCEs with some ground in situ measurements. So what we validate against is molar ratio density, which is a fire released NO2 and fire released CO. So the reason we choose this molar density ratio is because the lifetime of the NO2 and CO is relatively long, and also the background NO2 is much smaller compared to the background CO2, so which will provide us a more robust data sets for the validations. So what you can see here is the EPA molar density ratio is positively correlated with MCE, which means the MCE derived from FADA2 has scales to to partitioning the fire phase. For example, here we can see it will be more flaming, and here you can see this event or these areas will be more smoldering. So how can we use the FADA2 in case of the modified combustion efficiencies? So as we discussed before, the FRP is the total power of the total energy released by wildfire to the space. So if you see the global distribution, if you see the global distribution of the FRP, you can see over the Amazon regions and over the tropical Africa regions, they have the highest FRP densities, which means wildfire happens a lot over these regions. However, by looking at the FRP distributions, we won't be able to know which part of the world is more flaming, which part of the combustion of the wildfire will be more smoldering. By looking at the MC distributions derived by the FADA2, you can see, although in terms of FRP, Amazon regions and subtropical Africa areas have some kind of same strengths in terms of the burnings, but the combustion efficiency or the fire phase is way different. Because the subtropical area over the tropical Africa is mainly dominant. Land in terms of land surface type is mainly dominant by the grassland ecosystem. So you can see it exhibits a much higher combustion efficiencies comparing to Amazons, which is dominated by the forest. And also you can see, we see several hotspots. For example, over the North Dakota, Texas, Russia, China, and also the Mid East. So those regions actually are the locations where gas flaring industry, oil cracking industries are most activate, which means they need to burn those gas for safety purpose. We call those burning the gas flarings. So you can see basically the MCE resonates with the land surface type. And what we can observe is the combustion efficiency for the gas flaring activities is greater than the grassland-like ecosystem, and then it's greater than the forest-like ecosystem. Which this observation is pretty true, because you can imagine by turn on your stove, you will see the gas flarings is very flaming. Comparing to the grassland-like ecosystem and a forest-like ecosystem, the canopy structures of the forest ecosystem is way complicated than the grassland-like ecosystem, which means in terms of the oxygen availability, canopies over the forest will block the oxygen flow or airflow, comparing to those grasslands. In grasslands, they are more like the canopy, the surface fire. So which means the airflow will be way easier to entrain into the fire happens on the grassland. So if more airs and more oxygen involved in the combustions, we will be expecting a more flaming fire, which is what we observed, from our observations. Grassland-like ecosystem will have a higher MCE compared to forest. So as I said, the 4.2 right now is is processed by NASA by NASA Goddard by NASA JSFC daily, and we will later practice on using a Python script to get the data from the labs. Another applications of the 4.2 product is a file progression mapping. So you can see here, this is the CODA file which I showed before. This is a file progressions for the CODA file. A and B is made from separately by SUMI NPP file product and the NOAA 20 file product. And the bottom panel is a file progression estimated by the National Forest Service. So you can see they are very much consistent with each other. Besides the MCEs, the VF defines the ratio also have a lot of merit. So what we are showing here is a file progressions in 2 consecutive days. So the dotted area, the color coded dotted areas are the FRP on the upper panels are the FRP distributions for today, let's say, and for day 1, and the shaded area are the file progressions for the next day. So you can see by looking at this map, you can barely find a relationship between the FRP and the fire progressions. However, if we look at the VF map, what you can see here is here this you can clearly see the fire line, which is usually the fire line will have a higher higher VF. So what you can observe is for areas that has a higher visible energy fraction, the progressions of the fire is much faster. Yeah. So if you look at here, and you can see in the second day, it progressed very much and almost double the burn area. However, if you can see here, if you can see on the right or on the east part, they have very low VF. So you can see they are barely progressed to this direction in the second day. At last, here, here is, we can also use the MCE to estimate the emission factors, and then we can create the MCE modulated fire emissions global wise. So you can here what you can say is a global CO. Sorry. Here you can see the global MC distribution for single days. So you can imagine CO emissions over the gas flaring areas will be much smaller than peatland biomass burning areas, for example, over the Indonesia and also over the Amazon regions. So we have come across the fire detection algorithm FADA2, and we will continue to talk about the impact of the atmosphere absorptions on FRP. After this short sessions, we'll have a break, then we'll come back to the hands-on practice. So let's come back to the idea how the FRP is estimated. So you can see, by definition, FRP should be calculated based on the temperature of each fire component. But as we mentioned, to know the actual temperature and the actual burning area of each fire component in an area is very difficult for us in terms of remote sensing, because what in satellite remote sensing, what we can sense is all radiance. So Dr. Martin Worcester come up a genius idea. What he did is he correlated the 4-micron radiance with T to the 4th curves, and then he found actually the 4-micron radiance is magically aligning very well with the T to the 4th feet. And then he proposed we can use the 4-micron radiance to estimate the FRP, which is great and has been used for the past 20 years. However, if we look at the how the 4-micron radiance is calculated, you can see it is two terms. First, it is governed by a radiance term and is weighted by its area. This radiance term is there are there are a lot of things involved in this radiance term. So we have the temperature and the wavelength determined term, that is Planck function, which is very clear and pure physics. In terms of satellite remote sensing, each sensor has its own characteristics. So we need to consider the sensor spectrum response functions. So the the fires occurs on the surface, and the sensor is in the space. So between the surface and the space, there is atmosphere. So light will propagate through the atmosphere, which is a medium, and this media will have some transmittance. So we will talk about the impact of the transmittance here. So you can see the radiance term is modulated by both the atmosphere transmittance, emissivities of the fire emitter, which is mostly 1 for most of the case, the temperature of the burning itself, and also modulated by the sensor characteristics. For the most of the time, we know the sensor spectrum response functions, and we rely on the temperature, and also the 4-micron radiance, and we assume in most of the cases, the emitter for biomass burning, the emissivity is 1. However, the atmosphere transmittance is complicated. So here, what we are showing is the atmosphere transmittance for each rear span. So let's simply look at the 4-micron radiance, 4-micron channels. So you can see the black line is a transmittance, is an atmosphere transmittance in standard summertime, mid-latitude summertime. So you can see from across the 4-micron channels of the virs, the atmosphere transmittance vary from 80% all the way maybe to 55%. That means the 4-micron radiance emitted by the wildfire will go through a lot of attenuations. Then let's further look at the contributions of each atmosphere components to the optical depth or the transmittance. So you can see N2 nitrogens contribute around 70% to the optical depth. However, what we can see is nitrogens is a very stable atmosphere trace gas. Oh, not trace gas, actually gas. Is a very stable component. It won't vary that much. So as a CO2 and N2O to some point. However, you can also see water vapors contribute maybe 70% to the water vapor contribute around 70% to the optical depths on 4 microns. Although water vapor in the standard standard mid-latitude summer atmosphere profile, water vapor contribute only 77%. However, water vapor itself is a highly varied, atmosphere trace gas. So think about, if it rains, the water vapor in the air will be increased dramatically. And in a dry environment, the water vapors will drop a lot. However, in terms of nitrogens, it will mostly keep consistent, no matter it is dry or wet. So this is to say, the water vapor is a large has a largest contribution to the variations of the of the atmosphere transmittance. So the atmosphere transmittance or absorptions will contribute to will cause two facts of the FRP estimations. So what you can see here is the angular distributions of FRP globally. So you can see at the nadir, the FRP is always higher than the end of the swaths. And you can see, there are some kind of follow a bell shape. On the other hand, so if the sensor response function of the two different sensor is are slightly different, there will be some inconsistency or on the FRP retrieved by two sensors. So what you can see here is we compare the FRP estimated by the swimming PP virs and the NOAA 20 virs. So you can see there is a systematic difference. There is a systematic differences around 1.3 no, sorry, around 0.4 megawatts differences. And also, from the regression lines, you can see, we have a 0.3 or 3.5 offset. So this is to say the atmosphere absorptions affect the FRP a lot. So we need to consider the corrections of the FRP, the corrections of atmospheric absorptions on FRP. So what we did is we calculate the one-way transmittance as a function of the precipitable water and view geometry, view zenith angle. Basically, for each of the view zenith angle, we calculate its satellite, its in atmosphere, its transmittance. So you can see very interesting. So the transmittance actually decrease as the increase of the precipitable water. This is pretty reasonable because if you increase the total amount of water vapor in the air, the absorption will be stronger. And also you can see as the increase of the satellite zenith angle, the absorptions will also be stronger. This is also reasonable because as the satellite zenith angle increase, the length, the light path of the light path increase, which will enhance the absorptions. So what we found is, for MODIS sensor, the absorptions is around 10% in the nadir and around 25% at the end of the swaths. In contrast, for virs, because for virs, you can see here, it is more towards the water vapor absorption band. The water vapor absorption at nadir is stronger, is around 30%. And towards the end of the swaths, the atmosphere absorptions contribute to 50% to the signal attenuations. So with this, lookup table, atmosphere transmittance lookup table generated, we're able to correct the attenuations. So we use the view geometry together with the water vapor content from the NASA geosystem as a proxy of the water vapor content to correct the angular absorptions on the 4 microns. So you can see after corrections, let's directly look at the panel B. So the dotted line, as I showed here, is the FRP angular distributions before corrections. It is a bell shape, basically is a cosine shape. After corrections, you can see there's some kind the distributions is some kind of flat, which means we successfully removed the impact of the absorptions to the 4 microns so as to the FRP. So this is very important because if if this is very important because you can imagine if your measurements have some systematic and periodical errors, just like this a cosine shape, you in the application of this data, you might introduce those systematic and periodical errors into your downstream applications. However, after corrections, those systematic errors is gone, so which will provide more, which will make the input more reliable. More importantly, after corrections, the intersensor discrepancies is mitigated. So you can see here, this is a full size this is a full view size of this figure. So you can see before corrections, there is a systematic bias between the NOAA 20 and Sumin PP FRP. However, is around 0.6 or 0.4. However, after the atmospheric correction, the differences is gone. And also you can see the correlations got improved and the slope, got mitigated. So finally, let's have a global view of how the atmospheric corrections will contribute to mitigate the problem, the FRP distribution problems. So you can see here, this figures, the top figures shows the FADA2 global FRP distributions. So the second panels is FRP increment due to atmospheric corrections. You can see over the Africa regions and also the India regions. Those regions are grassland-like. India is more like cropland, is also a grassland-like ecosystem. So you can see over those regions, the increase of the FRP are most significant. On a global sense, around 60% of FRP, 60% FRP increase is achieved during for the atmospheric corrections. So this is pretty significant. So if we look at this equations, if we look at these equations, we will know the biomass burned is proportional to the FRP. So with this increment, we basically reduced the uncertainties that existed in the FRP. Then that means we will further reduce the adjustment to the biomass burn coefficient, or the fine tunings of the fine tunings for the fire emission inventories. Consequently, we're expecting we will have a better forecast capabilities if we correct the FRP before ingested into the fire emission inventories. So I guess, this will be the end of the second section, and we will come back maybe 10 minutes later around, 11:20. Um, I guess everyone now can see my screen. Uh, it is a pure screen sharing, not slides, and it should be a Chrome browser.
I don't see a Chrome browser.
Excuse me. Give me 1 second. Wow. How about now, Megan?
Yes.
Okay. Yeah. Thank you. Thank you very much. So hello everyone. This will be the third session, and I hope this session can be short. So as we discussed just now, in this session we will talk about three pieces of code, and I will walk through the first two, requesting using a script to requesting find out data from NASA data search, and a mapping of file progression use FADA2 product. And the atmosphere corrections script is we will also walk through it, but because it requires a large amount of data, we won't do demonstration here. But if you have any question, you can send me emails or send emails to any of the co-authors listed as corresponding authors in the paper. Yeah. So we will first look at the requesting FADA data from the NASA Earth data search. Let me make this larger. And what we will use is here, what I will use is Google Colab. And let's first look at this the AMS Satmoc active fire Git repo, and we just click it, okay. And I will actually not need this. And then what we would do is do it from scratch. You can simply Google Colab. And for the first one, you will see the first option, welcome to Colab. And let's just go there and let's create a Jupyter notebook. Download folder and new notebook. Oh, actually, let's then rename it. I don't think Okay, so then if you go to your drive, you should able to see your Google Drive if you have, or if you are if you use a local if you use a local or Python compilers, you should see you should open a Jupyter notebook or a simple Python .py text text file. But if you are using the Colab, you should be able to see at your Google Drive and in your under your Google Drive there will be a folder called Colab Notebook. After you creating the Jupyter Notebook, and for a certain moment, you will see this the download Jupyter Notebook showed up. Okay. And first, let's install all the libraries we need, or at least we import. So here, a very special libraries we will use is the Earth Data Access. So this is NASA recommended Python libraries to download data from the labs. So with that, you can provide your credentials interactively, or you can also hard code your credentials. So let's first do it. Yeah, so you can let me close this one. So you can see, I hope you can see it very clearly. Okay. Yeah. So I guess we've installed all the necessary and import all the necessary libraries we need in this script. And then we start a new code session. And we just need to copy and paste all the functions. Okay, we just need to copy all the functions here first. And I will walk through with you all the functions. So here, the product is this. So if you look at this one, so on the Earth data search, each of the NASA product has an individual ID, and the individual ID is actually this ID here. So if you Google this one, if you directly Google this one, it will direct you to here. So you will know the concept ID. For example, what I'm looking for is VIIRS swimming PP 4.2 fire modified combustion efficiency product on SWAS level 2. This is a SWAS, because VIIRS is observed by every 6 minutes. Yeah, so it is level 2 data, and the resolution is 375 meters, and the processing versions is the second version. So we have gone through the first process already, and we this year GSFC reprocess all the land product. So we create. So right now the product tier is second version. So here so here you can see the coverage is global, and the most important thing you want to have is this ID. Because this will be the actual identifier for a product. So for the 4.2 is this one, and for 4.2 swimming BP is this ID. Let's say 240, and for others it could be different. But only with this ID, the API would recognize what kind of product you want. If you input a 4.2 modified combustion efficiency into the code, the API won't recognize it. You need to this. You need to this. You can also Google or conduct Earth data search to other product to download to get a concept ID for other product you are interested. and I'm strongly believe this this code will also work. So here we create a dictionary, a global dictionary that map each of the concept ID to the actual name, because with this name it will be more user friendly. VNP means sorry, assuming PP virs. IMG means 350 meter resolution. And here, I think I will only explain this. VJ1 means is NOAA 20 virs. MOD means 750 meters. Yeah. There's no systematic differences between the the MOD or IMG, because our FADA2 algorithm is generated holistically using M-band M-band observation and I-band observations. So the only differences is whether we aggregate or we sleep the FRP or not. But it won't change any of the scientific quantities or values for the detections. So here this one ensure driver is just a simple functions that map this collab with your Google Drive, because right now we are working on the Google Drive collab environment. We need somewhere to host our data, and the most convenient place is your Google Driver. So Google provide APIs that allow us to mount the collab with your personal Google Driver. But if you are let's say if you are working on your local computer, you don't need this one. And here is just a functions or helper that manipulate the daytime the date that you input for the data of interest you want to download the data. And here you don't need to look into detail on this one. Basically here what we are using is we call the Earth Access API, and we provide the Earth Access login, and then we search data in the Earth data, and then we download it. Let's first compile this part. Yeah, so I think it should be compiled correctly, and we start another code block, and then we copy and paste this main session here. And here the for user aspect, so the thing you need to modify, you need to modify is which product you want to download. You need to define an area of interest. For example, here what I'm interested in is campfires happened in 2018. So I specifically provide the boundaries of the campfires, and also I provide the start date and the end date for the campfire events, and I provide a directory that I want the data to be saved, and then let's run it. And here, if you are using a Google Colab, it will ask you whether you want to connect your Google Colab with your drive, and the answer is of course yes. Yeah, you need to click the yeah, you need to click yes. Yeah, so here, it asks you to only this time it will ask you to provide your Earth data login. And after that, if you rerun your code, you don't need to provide it. But however, you can see after I enter my Earth data login and the code begin to search data for me. Okay. So for example, on this day, on November the 9th, it found 1 granules of data. And the second day, it found 2 granules. And then here, it summarized, it will download 18 granules and it will be downloaded here. So let's go to my drive. Let's go to my drive. Give me 1 second. Yeah. So here you can see because I specify, I want the data to be saved in the file.data. So and basic here, in somewhere here, we actually make the directories under the mother directory we provide. Then you should see, okay, here, this one is created. Let's click in. Yeah. So you can see here, those data are fresh download, 2 minutes ago 1 minute ago when we execute the data. Let me open the. Yeah. So anyone have any questions or anyone have any hard time on doing this part? Or maybe, Megan, we should, let the audience, give the audience maybe 5 minutes. Yeah, we can. Yeah. And after 5 minutes, we can come back and, yeah, we can come back then do the next step.
Sure. There is a question in the Q&A. How do I provide or change my drive information?
Oh, give me a second. Q&A. How can I provide or change my drive? So are you using, so if you have a Google account, supposedly you should have a Google Drive, and the default drive amount is this content and a drive. By mount your Colab to the by mount your Colab to your Google Drive, the default default the root directory is is my drive. Yeah, you just need to then content drive and my drive, and you can do whatever blah 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 here, and this code will create the subdirectories. Or if you have let's see, if you are using so if you are using your local, if you work on your local machine, you don't need this. You just need coming out, and you provide output directly. For example,
So I think the follow-up question was, provided that they are using Jupyter Lab or PyCharm.
PyCharm is on your. So I guess
So if it's Jupyter Lab or PyCharm, but it's on their
it's
local
local.
computer, this is
Yeah.
still the correct.
Yeah, I think you just need to come out. You just need to come out You just need to come out and come out this one, and this code should be able to create subdirectories under the script, under your script. The at your location, at the directory where's the script you are saving. Another question, can you recommend a free software to preview those nested files and modify? The most convenient one is the panoply. Let me type panoply. Panoply. Yeah.
Just to note, Panoply is a viewer, but you won't be able to modify the netcdf files, unless I'm wrong.
Yeah, you usually we cannot modify a netcdf file. Yeah. How know the latest available product for monitoring wildfire? So good question. So the FADA2 product right now is processed by GSFC in near real time. So usually we are expecting a 2-hour time lag. So once the satellite overpass and once the level 1B data is available, we should be able to get the data. Yeah. Yeah. You can. So with this one, I think at our applications, we run the code 4 times a day. We run the requesting code data downloading code 4 times a day, and that will guarantee the full coverage. So for example, at this one, at this applications, we actually request the data. Yeah, as I said, 4 times a day, and it will allow us to have the full coverage, global coverage. So yeah. Yeah. I think we are good on the data downloading part. So if you have problems on accessing access the data, you can raise your hand, and we may find another way, to share the campfire data for you for the hands-on purpose. Okay. So if everything is fine, let's create another drive. This drive, we will explore the we will do the mappings. So of course, so let's rename the Jupyter notebook as map file.2. And in this one, because we want to map the data into we want to plot the data onto a map, we need quite a lot of other libraries. For example, the cutovize, the PyProject, and the Shapley. Yeah, which allow, and we may also need the X-array and the netcdf as a support libraries of the X-array. So in the Colab, everything will be super convenient. Yeah, just for hands-on practice. For your own research, and you can also install those libraries. But you might consider use version control or library control software such as Anaconda and others to Oh, this is a little embarrassed. Yeah, I think right now it's okay because in the I think we run into an error. That is because right now CutPy have some CutPy, which is a library we use to plot the map, has some problems, has some compatibility problems with the Colab. But by rerun it, we should be able to fix it. And here we've already installed all the libraries we want, and let's start another set code block, and let's import all the libraries we install and import. Let's import all the libraries we want. So of course we need OS and the globe, that is the libraries we use to find the files, and we use NumPy, X-array. We use X-array to read the data. Yeah, and we use matplotlib to plot the map. Yep. So again, we need to we can copy the code block here. So we mount this we mount this Jupyter notebook to our to your or to my Google Drive, and then we will specify, because as you can see, I save the file data. I save the data into the file underscore data. So I changed. Yeah, I provide the input date directly as this. Yeah, it will ask you to mount again. You just need to click. Yeah. Yeah. So it got mounted, and let's look at what kind of files we have. Yeah, see, we use a list.dir, OS list.dir, and to get all the NC files in the file.data directories, and we stored it. So right now, what you can see here is is the file data listed by time. And let's open one data first. The first data, okay, this one. So here, so this is the beauty of the X array. So you can see here, in this file, you have we have 1,787 fire detections. This is the dimensions of the files. And these tools actually, you don't need to care about the rest of the dimensions, because that related to the related to the QA flags, and also it is actually the dimensions of the input level 2 or level 1B I-band data. And you can see this data set has two coordinates. It is latitude and longitude. And then if we click at the data variables, you can see it has a lot of parameters. For example, we have the MCE, modified combustion efficiency. We have, let's go to this one. How about this one? Radiance. See, FP M13 radiance. It is 4 micron radiance for FRP calculation, and it provides you unit, and it will also provides you it is a projection method. And we will also have those attributes you can explore, yeah. And here it gives you what kind of input is used to generate these fire detections. So if you are interested in tracing back those data, you can explore it and download those data. Yeah. So we save each of the steps. We save all the steps in the metadata. So we've already the information, the metadata information can be found here. So I will share it, here. So the metadata information should be found in the user guide. And also, the QA, the algorithm QA flag, and the file mask bitwise information, they can all be found in the user manual. And in the user manual, we also provide some land surface type, because FADA 2 do provide a land surface type, and we also provide recommendations, when you use how you use the data. Okay. Okay, we cover this. When we have the data ready, right? Then we read the first data. So how about we just visualize what the first day data looks like. So here let's paste those data here. So the first two line is in order to map the FADA2 data on the ground, we need to define the extent. but we don't want, you know, the extent is exactly the fire spot. We want to include some buffer zone. The pad lat and pad longitude is doing that way. And here, you know, we calculate what is actual extent for the detection, for the fire detections. So this is very practical because for fire detected over the polar regions or near the polar regions, a swath, a satellite files may cover a very large areas. If we use Planck Korea projections, that will, you know, make the graph very large. But maybe, you know, for the most of the areas, there's no fires. So we, you know, we are, you know, you are such, you know, you are recommended to you to derive the adaptive, you know, extent for each of the fire detection product or files. So with minimum and maximum lat long, you know, derived, you know, we can set the extent. We can set the extent, and we create the plot, you know, in a traditional, you know, very classic, you know, Python style, and then we add some map features. Okay, let's first run it and to see what happens. Yeah, so you can see here, the red dots are the fire detection on the first file. Do you want to know what is the first file? No, we can. Yeah. So it is this day. I believe it is December the 3rd, maybe. Yeah. So you can see for this day and or UTC 948, it covers the whole west part of the United States. And we will only, yeah, this is just, you know, use red dots to represent the locations. And we can also, because, you know, we can, it can easily got, you know, the location informations by looking at the coordinates. We can color code, oh, sorry. We can actually color code the location, color code the dots with some quantities we are interested in. Okay, so here, you know, let's plot it, you know, color code the figures with MCEs. Sorry. With FRP and MCE, and to see what it looks like. Here, you know, I provide two helpers. That is, you know, help us to create a multi-figures that contain a geographic axis, and also, you know, because we want to make our figure better, you know, we might want to align. We might want a better a good, you know, color bars. Yeah. So another helper is, you know, to add a horizontal color bar. And again, you know, yeah, we first remove, you know, we first remove those invalid data, and then we extract the information we want. For example, the FRPs and also the MCEs, and, you know, we do the practice we just mentioned. And then here, you know, we plot the map and color coded with different. Here you can see we color coded in the first image. We color coded with FRP, and in the second figures, we color code the dots with MCEs. Let's plot it. Okay. Yeah, so you can see here, we successfully plot the MCE and FRP. So you can see here. Here, we limited the FRP, the maximum of FRP to 10. So because for the majority of the fires, it can be small. But you can see, there are certain fires. For example, over here is campfires. And over here, they are large, some dots. This is not very apparent because, we are on a very, very, very large zoom level. Later, we will focus on the campfire and you will see the details. So you can see here over these regions, the fire is some kind of large because, they generally have some large fires. That is campfire. We know campfire is large. It destroys I think it might destroy the paradise, maybe. And here, in terms of MCE, you can say over here and here, the MCE is extremely high. So this is because this regions is some kind of gas flaring stations. Yeah. So we mapped the fire detections. Then how about we look at the campfire closely. So let's directly first execute it. Then we can come back to explain the code. Give it a second because we are doing something interesting. So okay, so here is a mapping of the campfire using the FADA2 product. And let's first look at the image, then later we can explain it in detail, the code in detail. So again, see, comparing to the maximum values of 10, here I set the maximum to 30 to 30 to allow a larger dynamic range. Okay. So you can see, for the first day of the campfire, it starts, it has a relatively large coverage. It spread, very broadly. So you can see, the fire actually is pretty heavy over these regions, but they are not in the edge, right? You can see, they are somewhere in the middle of the events, here and here. As we say, FRP is a total strength of a fire event. It is not that representative to the combustions. However, so if you can see here, if you see here, this one is the MCE. You can see here, for those area fire is large, actually it is not that flaming. And for those areas that has some kind of smaller FRP because it is in a fire front. It is in the initial combustion status, and it should be some kind of flaming. So you can see the MCE here is pretty high compared to the rest of the fire events. Okay, how we do that? So we also map the fires on a Google map. So here, we need this Cuttlepy image tile services APIs, and we import it here, and we do the practice. We mask out those null values, and we set the extent to the campfires. And here, we end we end the Google type Google image. So you can choose satellite or terrain background or whatever style you want. But here I choose satellite, and here we plot. For the first one we plot the fire radiated power. For the second one we plot the MCE. Yeah, and then you can see the fire now. But if we further zoom in the data, you can see here there are some kind of blurred, correct? There's some kind of blurred compared to these regions. Those dots are very clear or separate with each other, but here those regions are blurred. This is caused by the bow tie effects we discussed. So we need to further remove the bow tie effects. How can we do that? To remove the bow tie effects, we just need to add another criteria. Let's add another code block. We just need to add another. So the bow tie effect is the overlapping between M band. And as I just introduced, what we use the data band frames as reference frame to detect the bow tie effects. So the more area that is overlapping with the more area of M band pixel that are overlapped with the data band, the less bow tie, the less impact it is affected by the bow tie effects. So here we use 0.5 as a threshold, which means if a pixel is only 5% overlapped with the data band, we will treat it as overlap or as bow tie effects. So let's look. And for the rest of the code, it is identical to the first one, and let's execute it to see what happens. Okay. So you can see here, over here, they are very much separated, right? So if we go back to here, there are some kind of connected. But here I would say, depending on the parameter you are interested in, so if you are interested in the burn area, the statistic of the burn area, you might not need to filter out the bow tie affected pixels. But if you are interested in the FRP bulk statistics or the MCE bulk statistics, you might want to filter it out. Okay. So with this code, we mapped 1 day of fire detections, and then the next task is we combine all the data, all the maybe 18 days data to create a fire progressions. But because creating a fire progressions is a little complicated than mapping 1 day, we will first do the data processing. So this block of data is we define a helper, and we extract the observational day of each files, and then we concatenate the file files from a single day. That means, for each day we will just have one array to plot. So yeah, then we loop through files and we save. Here you can see we save the data. We save the data the data in the same day into one entries of a dictionary. Yeah, with that, then we can oh sorry. With that, we can map the data on the map. Again, here, we create map. Because we are plotting the progressions, we only need one figures, and this is the decorations. This is the decorations, and this part is and the Google map, and the Google map background. And here, we use colors to indicate the progression of the day. Okay. And we desiccate the continuous rainbow base map color map into a number of days, and then we plot it, we plot the all data and the color bar. Yeah. So here, you can see, for the first day is somewhere here. And the second day, it propagate. And, for the last day, last day is some kind of this. So do you think, this figure is enough? So let's look at here. What National Forest folks plot, right? So they're creating very nice file parameters. How can we do that? So that in order to do that, we need to connect all the dots from a single day into a polygon. So in the last piece of code, I have the alpha shape helpers that can help us to do that. Let me first run the code for you. Yeah, we got the data. So you can see here, before, what we are doing is, plot each of the detections individually. And here, what we are doing is we connect those dots into a polygon. And, in this way, we delineate the impact area nicely, just as what the National Forest Service do. How do we do that? How can we do that? Basically, what we did is we use this alpha shape helpers to connect those dots. We first connect 3 dots to create triangles. Then we further concatenate triangles. Triangles use those convex algorithms. Yeah. So here, but for you, if you are just a pure user, not a developer, you just need to copy and paste this code and run it. So you can see here again, we group all the points by day. Okay, and then we first set up the background and of all the decorations, and here for each of the day, we put the points into the helpers, and the helper will concatenate all the dates together as a polygon, and then we visualize the polygon. Okay. there is a parameter that is alpha you might want to play with. Right now we are using 1,000 meters, but maybe we can try, what happens, if we choose 500 meter. Yeah, this one, this this alpha control how sharp you want your polygon looks like, and it should always be customized by each individual cases. For example, if we use a larger number here on the denominators, we allow the polygon to be connected more broadly. So you can then you can see here it results a little bit different compared to this. But from my from our application here for the campfire, 1,000 would be enough. Yeah, so you can see with this, let's compare this one and this one. It nicely keeps the detailed features of the fires, but also it's some kind of the fire progressions, but also it's some kind of spatially smoothed. Okay. And here we can further, for example, we can further overlay this one with a second with the next day polygons to highlight how the fire progression will respond to the MCE or FRP, just like the figure, just like the research we did over here. Yeah, I guess with these capabilities you can do a lot of interesting research based on your own interest. Yeah. The last part of the hands-on session is FRP correction. But I think the FRP correction itself is very straightforward. Yeah. So you just you just need to prepare your file data, and you need a lookup table which can be accessed at this site. You just need to click it. Okay. Then you provide the water vapor perceptible water vapor database. For example, if you want to GeosFP, yeah, you provide the GeosFP. Then you just call the data, and it will do the atmosphere correction for you. Because here we need a GeosFP data, and GeosFP data is relatively large, so we might not do the demonstration here today. But if you look at the do FRP code, you will see here it gives you options. If you to see if you want to use if you really want to use the forecast water vapor content, or you want to use the default water vapor content. Yeah. Yeah. So for example, you can see here, for each point, if you provide the FRP, if you provide the water vapor content from the model, it will use GeosFP water vapor content to conduct the atmosphere correction. Otherwise, it will assume a typical value of precipitable water, which I believe is a mid-latitude summer atmosphere profile, to conduct the atmosphere profile, or to conduct the corrections. Then it will output the FP power atmosphere corrected for you. Yeah. So yeah, I guess we are done for today. And if you have any question, you're welcome to send me questions to my email. Yeah. Otherwise, let's call it a day. Thank you.